Yep, hello. Welcome to MATH1081 Revision Seminar, Part 2. So I'm Marcus, and I'll be taking us through the topics 2 and 4. So let's just get right into the first topic, integers, modular arithmetic, and relations. Alright, first off, given that 307 is prime, find 303 to the power of 306 mod 307. So here we'll be using Fermat's little theorem, because otherwise that's it's not really viable to do by hand, so you've got to apply this theorem. It's actually originally given by it's actually originally given by this, but given that P does not divide A, we can actually simplify it to this one on the left here. So just applying this formula really, we can see that it really simplifies down quite easily to become 1. Very nice and simple for this first question here. I mean, yeah, all you're doing is you're just applying this formula. Obviously you have to check that 307 does not divide 303, but that's quite clear in this case. Now we've got a slightly more complicated one, a greater power, 303 to the power of 306, 3063 mod 307. So we'll be applying the same Fermat's little theorem again, but we'll also be using the other rules that we've learned so far. So yeah, so we start off by just using our result that we got in the previous question. And we can rewrite the more complicated power exponent and just split it up into what is much easier to work with. So if they give you a question like this, it will be nice. It will most likely be like nice numbers. Like you can kind of see the connection here. Maybe it's not to the power of 10, maybe it's 3 or 4 or something. But you just have to look out for this, and then you will be left with a smaller power, which you still have to deal with. In this case, we can see like 303 mod 307 is clearly -4, and yeah, just applying the rules that we've learned in this course, like that is the same as we can just do that to the power of 3. Of course, 1 to the power of 10 is just 1, and then we can just make it a positive, just to give a nice clean answer there. So that should be fine. Moving on to the next question. Yeah, so there's like a few sub-questions to this original Matthew was trying to solve a modular congruence. Hopefully this should be familiar to most of you. It was in our lab tests and you should have learnt it, but we'll cover it again. So this first question is just asking us to find, essentially just find one solution with the modulus, but we can break up the question first. So first we will apply the Euclidean algorithm to find the GCD of 36 and 208. So just remember the Euclidean algorithm. You're just basically you're just breaking down the larger number and then getting a remainder and just repeating this process until eventually you get the remainder to be 0. And you can see that like our last term here will be equal to the GCD. So hopefully you can see how we've worked through this. And going back to our original equation here, this the modular congruence, we want to find a solution for x, and the pattern with these questions is that you make it into this format, which is much easier to work with. So really what taking the mod of this means is that there's an integer k, right? And I've taken to the other side, I've named it y, right? Because, well, k is like negative y. It's just nicer to have the addition here. And then in this last step, I've seen that I could divide the equation by 4. That's because the GCD is 4. But you have to take note that not always will you be able to divide this this number here by 4. So I've just done it because I am able to. And then now that it's in this form, we can use Bezout's identity. So if you just read that, it's basically saying that there are integer values. So we know it will work in this case because if, say, we apply Bezout's identity to this, well, we know that the GCD of 36 and 208 equals 4, right? Which means that there will be integers that will satisfy the equation 208 equals 4. And then we can just multiply everything by 25 and then you will get 100. So that's the process that we're going to be working through. So first of all, I'm just going to take the previous Euclidean algorithm that we had and I'm going to divide every term by 4, just because it's a little bit, you don't have to do this, but personally I find that it's just a little bit easier to work with these simpler, smaller numbers. So just to reiterate, this is the exact same Euclidean, this is the working out for the Euclidean algorithm that we had right here. And yeah, I've just divided every term, I don't know if I clicked, yep. Every term by 4. Now, there is actually a trick that, in theory, you could just kind of look at this equation, and you could probably see that, well, at least it divides by 2, right? Because they're all even numbers, and then you'll see that again, it divides by 2 again. So you could just divide everything by 4 in the first place before you've even done anything. That's what I would do, because it just saves a little bit of brain power when you're doing this Euclidean algorithm. So now that we've done that, in order to find the integers x and y such that it will equate to the GCD, we have to apply the reverse Euclidean algorithm, which is as the name suggests, it's the Euclidean algorithm in reverse. Basically, we start from this bottom line, and this bottom line, and we'll just, so in this, now that we've divided by 4, the GCD of the two numbers, which has become 52 and 9, is 1, right? But the same principle applies if it's 4, if we use the equation before we've divided by 4. So if we didn't divide by 4, if we're using our original and we wanted to be slightly larger numbers for some reason, then the process is you're just breaking down writing down the smaller number as a term, as a combination of the slightly larger ones. So obviously we start with 4, and then we'll take 8, because that's our next one, and we'll rewrite 8, and you're just slowly working up this ladder, and then we'll sub in 28, and eventually we'll find that our equation will be in the form that we want in terms of only 208 and 36. I've done the reverse Euclidean algorithm with the smaller numbers because I find it's just much faster to do, like in your head or in the calculator. So I'm just repeating this process of substituting in. So 1 is the GCD, so this will always be the same. So yeah, I'm just going from this bottom line. I'm just rearranging this bottom line to become 1 equals 7 minus 3 times 2. Oh, yeah. And then I'm substituting in here. And then, sorry. Yep, sorry. So, and we're just repeating this process by, once again, we're just substituting in for the smaller number. And if you substitute in for the smaller number each time, then eventually you'll get the bigger numbers. And we're just repeating this process until eventually we get to the final line, which is the form that we want. Just pay attention to what is the number you want and what is just the coefficient. Like, we want 52 and 9. It's not 52 and 29, right? 29 is the coefficient. And also just a quick tip, like if you can just double check like as you're going, because you don't want to get all the way to the end, but you can just check like the last digit. I find is the best way of doing that. Or you can just do it in your head. You can clearly see this is 36 and this is 35, so we're still on the right track. And then for this is just checking the last digit. This is 9 times 9, so it's going to be 1 is the last digit, and 5 times 2, the 0 is the last digit. So we're on the right path. And you can obviously just chuck this last line into a calculator if you have a calculator. But this isn't the final form that we wanted. We need to multiply by 25, because remember that on the right side here is 25. We currently have the integers for this equation, which is, obviously not the same equation as we want, so we just multiply every term by 25. So, as you can see, our coefficients become this, and now we have to link it back to, we have to think about, okay, what does this equation actually represent? Or you can apply like we're just like reversing this step again. 25 mod 52. Okay, so that's what we're really doing. X 52. So we've got this large number, but we take it to the mod of 52, because that's what the question is asking. The question is asking the smallest possible modulus. The smallest possible modulus means that we've divided by the GCD, which we have, to get 52 is the new mod. And with respect to mod 52, 725 becomes 49, and that's your final answer for this question. So just repeating that, so we just use the Euclidean algorithm to find the GCD, and then we change it into this form, and then I just simplified the Euclidean algorithm. You don't have to do that, but I find it easier to work with. We applied the reverse Euclidean algorithm to get the values of the coefficients, and then we had to multiply by 25 because this is we wanted to create 25, not 1. So that's that question done. Jack, so we've got someone talking about top laners, right? So this next question is a continuation of what we just got. So reiterating what I've said before, like the GCD has to divide the GCD of A and B has to divide C. Otherwise, there are no solutions. Like what we've done just won't work. There won't be integers which will get us to C. And if it does divide C, then the number of solutions is equal to the GCD. So in this case, our GCD is 4, so that means there will be 4 solutions. And the way you find these solutions is, well, I've just rewritten what we've got. So we've got the original, and we've got our GCD is 4. And yeah, we repeatedly add m over d, so m is like the modulus, until there are d solutions. So we just take our first solution, and we can apply this formula, or you kind of think about it logically, right? And this will give us our solutions, our set of solutions. Because in our previous question we had only gotten one solution, and that solution was with respect to mod 52, but I was asking us to find with respect to mod 208. So that's where we have to do these steps. So yep. Okay, hopefully that's all good. Right, so this is can be a bit of an intimidating question at first, but they walk you through it. So this is our first question. It's basically asking you to find A and B, and we're just using this substitution here. So this is just like the setup to the question, really, and then they're just going to walk you through step by step. So so what we can do is we just have to use a substitution here, because I mean we can see, I mean we've got a t here, and we've got two equations. We've got x and t, so it's pretty much the only step forward is to do this substitution, and we can see what happens. So we can just sub in and expand the bracket, and then we can divide everything by 1367. And dividing by 1367, luckily this very nicely just turns into 3. And yeah, this becomes this becomes this, yep. And now we can observe that, well, mod 1367, obviously this is going to be congruent to 0 because it's multiplied by 1367, so we can actually just get rid of this term, and then we can just rearrange this equation, and that's going to be our final answer. And we can just look back at the form. It's A and B. So it's just applying the rules that we've learnt, right? We can just divide the entire equation by 1367, and then this will cancel out, and now we're left with a much simpler form. Okay, and then this is just a question. It's kind of like a small theory question as to why. As to whether or not our equation actually does have a solution. And we can just refer back to this. So, I mean, 1367 is prime. So the GCD of 1367 and anything will just be 1 because it's prime. 1367 is prime. And so the GCD of 1367 and A will be 1 because it's prime. And this will mean that, well, because our GCD is 1, then obviously it will divide into B because, I mean, it's 1, so it's going to divide any number. In the original question, they give you like a bunch of options, but this is the only one that is that actually matters. So the reasoning is that A and 136 are relatively prime because, yeah, the GCD is 1, so it will always divide this number here, so there will always be a solution. Right. Right, so now it's just asking us to solve this. So it's going to be similar to the question we did earlier. We're just going to apply the Euclidean algorithm. You know, if you're watching this, maybe you can, on a replay, I think most people will probably be watching the recording, so you can always just pause and then check your answers. And then once again, we're just applying the reverse Euclidean algorithm. And eventually we get to a solution for t. So it's all the same ideas as before, right? We're just like finding this greatest number and then with like a positive remainder, and we just repeat this step again until we get the GCD, and then we will reverse the steps by obtaining equations for this smaller, so you're always going to be subbing in for the smaller one. This equation is what is this for? It's a very general question. So, and then you can just sub in here, and eventually you work your way up towards the larger numbers. And this will be our final answer. 153. And then it's asking us to find a solution of the congruence of this. And remember in the beginning we just subbed in x equals. We subbed in this for x, and we have a t now, so we can just sub in the t and it will give us our x. So in the end, I mean, this looks like quite intimidating at first, but they walk you through it and eventually you can find the answer. So it's just reverse Euclidean algorithm, and we had this simplification earlier. Right. But now they've asked a much more, they've asked for this question requires like a much deeper understanding of the rules and of the ideas that we've learned. So this is the credit for this solution actually goes to Gerald Bruce. Thank you. But hopefully you guys can understand what the thought process is. So basically it's asking to prove for every n there's going to be a solution. So we'll, just to establish the question, we'll just set up some, just define some variables. So you will just be like a solution. And then we can consider, because it's a solution, it will be, this is an integer times this, because that will still be the same, because we're taking mod 1367k. Obviously this term, if you're putting it back in here, this term will obviously cancel out with respect to this mod. So now that we've done that, we'll just see what x squared is. So we're just expanding this bracket. And the idea behind this proof is actually proof by induction. So hopefully you've gone through that in the proofs topic, which we covered in part 1 of this seminar. So obviously we were just going to be trying to look to cancel this term. So yeah, obviously proof by induction, so we're going to be looking at k plus 1, and we can see that k plus 1 clearly divides 1367 to the 1367 to the k plus 1 divides 1367 to the 2k, right? So we can get rid of this term. Okay. And now we will sub in and we'll get this expression in x. So we've just like this over here, like this u squared, it's become 388 and also become this n over here. So now we've simplified it further. And now we still have to prove that this term, well, basically we want to prove that this term is congruent to 0 with respect to this mod, which means that this will, we want 1367 to divide this term so that we can get rid of this whole thing. Okay, and then now we're going to be proving by contradiction. So we'll show that it, we'll just assume that it does not divide and then see what happens. So obviously if it does not divide, then there'll be like the quotient and the remainder. Like the remainder is key, right? And putting this in, yeah, so now we just sub in this as this, and obviously this 1367q term will be congruent to mod 0 with respect to this mod, right, because it will become k plus 1q. So we're just left with this remainder here. And then, as we've said before, as we've initially stated, 1367 does not divide this remainder. And because 1367 is prime, this implies that this and r are co-prime. Hopefully that makes sense, right? Like 1367, the only factors are 1 and this, right? So if you took this to a higher power, still, and it does not divide r, then still, if you take this to a higher power, r and this higher power will still be co-prime. Right. And because like this mod and r are co-prime, then there will be an inverse modulo, right? And we just denote this as L, and then we can multiply both sides, and we'll see. Obviously, this will it's the inverse modulo, right? So this r term will disappear, and the side is 0, of course. So it will remain as 0, and then this will imply that this, which is clearly wrong, so it's a contradiction. So, like starting from here is where we started our contradiction, where we stated that 1367 does not divide n plus mu, and following this, we saying that it doesn't divide means that we have this r, and because r and 1367, because 1367 is prime, r and 1367 to the power of k plus 1 will be co-prime. And because it's co-prime, we have the inverse modulo, and then you find that you have this contradicting statement, which means that this, our initial assumption, was wrong, which means that 1367 will divide n plus 2 mu, and because it does divide n plus 2 mu, you can see that this term here, if this is 1, 3, 6, 7, n, we probably shouldn't pick n, I'll just pick y, okay, then this term here, because it becomes 1, 3, 6, 7 to the k plus 1 y, and obviously in respect to this it becomes 0, which means that we will get this 388 mod 1367 k plus 1. And going back again, we were proving by induction, so we've now proved the case for k plus 1, and obviously originally we proved the case for 2. So it follows that, for 1, so it follows that for every positive integer n, this has a solution. So it's a very complicated proof, so you probably will be pausing and rewatching that many times. But yeah, this question is, testing your like the deeper understanding. So if you're only trying to pass, which you should obviously be aiming higher, trying to see what you're capable of. But if you're only trying to pass, then this can be quite a difficult question, because it also combines ideas, mainly from the proofs topic. But yes, it's a very thought-provoking question. Yes. And that's it for the modular arithmetic, so we'll move on to the relations now. Hopefully this proof all made some sense. But yeah, so these are just some basic properties of relations. So hopefully you're familiar with these, but just a quick reminder. Of reflexive, symmetric, anti-symmetric, and transitive, what they mean, and also what equivalence relation and a partial order is. Basically you just, yep. Okay, so this question is actually basically the same as what was covered in the last seminar, so just like some changed digits. So if you already watched that, then you can just skip this part. The 20 as in the last seminar is in the 2022 term 3-1. But maybe you prefer my explanation. So obviously equivalence relation, we'll just get started. We've got this relation here with this function, and we just to prove that is an equivalence relation. So going back again, that the equivalence relation is reflexive, symmetric, and transitive. So when you're proving that it is something, you need to use like general terms such as x, right, that you can't be subbing in particular numbers. If you're proving that it is not, then you can obviously find like one case in which it is not, and then that's sufficient. But for when you're proving like you need to use the general case to prove that it is. So yeah, the relation is if this function is for this, if they are equal. Clearly that will be the case for reflexive. And symmetric, yep. We've got this equals sign, so that's expected. And yeah, so symmetric is just like replacing this. The same thing, it still exists. And then transitive, I'm sure you can follow the logic states of this and this. then x will be related to z. And yeah, I mean, once again, the equals sign is an equivalence relation, so this is expected. And now that we've proved it's these three, we can say that it is a equivalence relation. Okay, and now we need to find the equivalence class of 0, which just means it's the it just means it's equivalent, like they will use the same output. So first off, we're just gonna find what does 0 actually give us, and so we're just subbing in 0 into this function, and that gives us -79, and then we'll just be solving for this. So we just set f of x as to be f of 0, and we solve this, and it'll be a nice factorization. So we can state the equivalence class here. Should be quite straightforward. Okay. Does there exist an element x such that the equivalence class of x has 2 elements? So if you imagine this graph, right, it's like a positive cubed graph, so it'll be something like this, and we'll also got the equivalence class, so we know that it does actually pass through the x-axis. And just like sketching this graph is really useful. Obviously you don't have to draw it out, like if you can imagine it in your head or something, but this is just like the general like positive x squared, and obviously with this knowledge we know it passes through the x-axis. So does there exist an element x such that the equivalence class has 2 elements? So that just means like when you're drawing for like a particular y value, there is just 2 points, 2 values of x. So you can see like most lines you'll draw will have like will have just 1, right? But you should be able to see that like clearly at these, well, I can't draw it very well, but clearly at these turning points there's equivalence class which only has 2 elements. So that's what it's saying, there's just like 2 values. So it doesn't actually ask us to in this question, it doesn't actually ask us to find, it just asks us to explain why. But yeah, you just have to differentiate and you can find the points. So I think that's should be self-explanatory. Okay, now we're moving on to this great fun Posset divisibility relation. This guy, you've seen these before. So we're going to be drawing some diagram. Find the maximal elements and whether or not there's a greatest element. So when I'm drawing these I actually don't know the pronunciation, Hesse diagrams. I think that's what they're called. I find it easy to start from, I mean you can just decide for yourself, but I think it's easier to start from the bottom, I think. I will start. Haven't given myself that much space. Okay, I'll go like this. 7, 19. And it's a differentiability relation, so first off we'll be dividing, like we'll be checking does 133 like connected to 19 or connected to 7. Basically I just start from the bottom and then check does this divide, and then just check for like each term lower, and then eventually you'll get your whole diagram. So to begin with, conveniently this divides both. And yeah, maybe you can just draw this out at the same time as me, because it's going to be a little bit of time. Oops. Right, so I've come across my first term. So if when you're drawing these, it is a partial order, so that means that it is transitive. So you don't have to draw these lines between like 7 and 2527, because like it's already transitive and you're already like passing through 133. So, yep. Very messy diagram. Okay. Maybe this is a better way to draw this. And 8. Okay. Oh, sorry. What am I doing? Don't know how I've done this. Okay, hopefully that's right. It might be wrong, but regardless, what really matters is the what we're actually working with. So the maximal element. So maximal element is just an element which doesn't go to anything above it. Like it doesn't have any upwards lines. So in this case, we can see that our maximal elements will be this, and this. And a greatest element is if there's like only one. So if they all like came into this one maximal element. But we can see here that like because there's no like connection between these, then like there's no greatest element. I believe so. Okay, and now it's a very similar question, but we're finding the minimal elements. So the minimal elements, as the name suggests, you probably tell, is these elements which don't have anything coming from below in your diagram, right? There's nothing that divides in this case 7 and 19. So 7 and 19, and yeah, similar to, well, it's not asked in this question, but we don't have like an element which is like it all comes down to this element here. So our minimal elements will just be 7 and 19, and then finding the upper bounds of 7 and 19. So these are like, they are both connected to 7 and 19, so it will be 133, and anything above and connected to 133, which in this case is 2527 and also 3059. So our answer for the upper bounds of 7 and 19 would be the set of three numbers here, and the lower bounds of 25 and 30. So the lower bounds of this and the lower bound of this, it's just once again where they're both connected, so 133, and everything below that, so this and this, so I believe that's 3, 7, 9. Right. So, I mean, for these, I would just recommend some practice. Hopefully I haven't made a mistake in this diagram, but regardless, I hope you can understand what is going on. But yeah, so that's the end of this topic 2, which is good. It's been exactly 1 hour. And I will continue and be doing the next topic, combinatorics. So, all these questions are actually the same as the 2022 Term 3 Revision Seminar. So if you've already watched that, then maybe there's like not that much point in watching this. Unless you really like my explanations. But, yeah, I'll just be back in just a quick 2-minute break. And then I'll be back. And we'll do this topic 4. Alright. Combinatorics. Perms and coms. Plus some other stuff. So yeah, once again, it's me, and I'd like to state that all of these questions are the exact same as the 2022 Term 3 seminar. Just that it's been real last minute this term, so if you've already watched that, then, unless you want if you want a second explanation on some question you didn't get, then you don't need to watch this, but if you can watch that, then hopefully we can get through these questions. So, starting off, 5 points, and we need to prove 5 points with integer coordinates, and we need to prove that at least one midpoint as integer coordinates. So pigeons, you should love some pigeons, mate. Pigeonhole principle. So hopefully you guys can understand this. N plus 1 pigeons and in pigeonholes. I actually don't know, why it's pigeons and pigeonholes, but you can think about this in any way you want, Maybe you got you've got 10 pieces of gum and you've got 9 friends. Well, clearly someone's going to get more than 1 piece of gum, And yeah, just keep in mind it's ceiling, you're not rounding. That can be a common mistake. But yeah, so going back to this question, basically there's we can just define the what the midpoint is first, right? And then you just gotta have a little bit of a think about it, and then if in order for like these numbers to be integers, either both the numbers are odd or both the numbers are even. Right? And then we find that, well, there's only 4 cases, right, in terms of odd and even. And we have 5 points, so that means there must exist. So these are our pigeonholes and these are our pigeons. So obviously one of these will have the same in terms of odd and even, you know. Like the 5th point will be even or even odd, in which case if we go back to this, you know, that will be integer. So that's pretty, I think you should understand that. It's just 4 possible cases. And now we're moving into the real perms and coms. So obviously when you just want to try and break down the question where possible, because it's a bit, you know, there's no need to just try and do it all at the same time. So we just created these 2 sub-problems, right? We're going to first find 80 identical and 8 children, and then we'll find 40 distinct and 8 children. Right. So 80 identical, we can just create this equation, right, where each child, the number of balls that each child receives is one of these integers, a non-negative integer, and of course the sum will be 80. So I think this form is much more familiar, and we just use like this formula, and so n is 80 and r is 8 children, and using this formula we can see that's 87 choose, or a combination of 87 and 7. Yeah, so this is an important thing to note. And the next question will be, like, as in question B, will be look into a case where, you know, they get at least. But so I'll further explain this soon. And this is just reading 40 distinct lollipops among 8 children. So this can be a bit, well, we can't use the same technique that we just used, because now they are distinct lollipops. Before it was identical balls, so it was just the amount, but now this is also like the type, which actually matters. So we'll just give you this is the basic, the general solution. So the best way of thinking about this question is instead of what lollipops do the children get, right? Just think about it as, where do the lollipops go? So each lollipop, so lollipop number 1 has 8 options, right? There's 4. But, you know, if I drew 8 lines, it would be a bit too... Anyway, so one lollipop has got like 8 options to go. 1, 2, 3, 4, 5, 6, 7, 8 children to go to. Yep. Because then, I mean, it's clearly they've got 8 options, so it's going to be 8, and then the second lollipop the second the lollipop looks like a child anyway. The next one will be also have 8 options, and this just follows on until you're out of lollipops. So yeah, once again, think about it as where the lollipops are going, rather than which lollipops the one child gets. I feel like that makes sense. But yeah, you're just applying this formula. So when you're using these formulas, it's really important to be able to recognize in the question. Usually they're quite nice, and they just say, oh, distinct. And the children are also distinct. So yeah, you can apply this formula, but you just have to make sure that you're applying the formula in the right case, right? In this case, it was distinct, and in the previous case, it was identical objects, right? So now we have to combine this together, and it's just simple multiplication of the two cases. And that's the question. Okay, but yeah, now we continue, and we'll get the problem with at least one ball and exactly 5 lollipops. So obviously we can't reapply the exact same formula that we've just used, because in the formula that we've just used, the number of balls that the children receive can be equal to 0. In this case, it's at least 1, right? But maybe they'll ask at least 2 or more, right? So there is actually a shortcut for using, well, I don't know if it can be defined as a shortcut, but when you have, it can be I is greater than or equal to 1, then you can actually just use this formula. But really what this is a kind of simplification, but I prefer doing it the slightly longer method, I guess, so that you have a better understanding of what's actually going on. So what I would do is at least 1 ball, right? This could be at least two, or at least 3, or so on, right? These same principles will apply. So what we can do is we can denote xi as, okay, I'm going to pick 3 in this case. So xi equals yi plus 3. So in this case, we'll, yi is greater than or equal to 0, right? So this will mean, is right, yeah. So this is in the case that the question asks at least 3. So the minimum that each child will get is 3, and then obviously this is just natural numbers, so we can go just counting above that. And then what you do is you would sub this in, so you get x, so x1 will be y1 plus 3, okay, and then you just repeat this, right, throughout the thing, so each one gets at least 3, and then once you've simplified that, then you just get the same thing again, but it's y's instead of x, and you'll have 8 of these. You've subbed it in 8 times, so it'll be 24, so it'll be 56. y8. And then now that it's in this form, we've given it in this form, and we know that, as we've defined earlier here, yi is greater than or equal to 0, then we can apply the formula that we've used before. We'll just scroll back up to it. We can just use this formula again, because we've created a situation in which it's the same form and it can be greater than or equal to 0. So this is kind of just showing you generally how to solve it. Obviously in this case it's only 1, so what we've done is you can actually use this shortcut because R is 8, right? And if it's at least 1, then it will be zi plus 1. And you can see that you will repeat this plus 1 8 times, and then you'll get like 72. 1 plus dot 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 z8. And then once you're at this step, then you reapply the same formula. I'll just rewrite it here. Plus 1 minus 1. And then you'll reapply the same formula and you find that you get 79. Which is 7, which is exactly the same as what you would get here. So basically this formula here is just a simplification of this step. But in the case in which they ask, at least 2, at least 3, in this case I've done at least 3, then you would do this. And then once it's in this form, then you just apply, once again you apply the same formula, so then it would be 63, choose 7. Right, so hopefully that makes sense. Yeah, so this is just the slightly faster method, I guess, but I think it helps to have this understanding of what is actually going on here, so you can apply it to more than, otherwise you'll just be a bit stuck if they ask any number greater than at least 1 ball. Okay, so moving on to the next part of this. So once again we've broken up the question into 2 parts, so it's much easier to just think one at a time. So, first off, maybe just think about it. Each child gets exactly 5, so it's not like at least or something. So, I think this is pretty self-explanatory. You just choose, 40, choose 5. And then, obviously, there's 5 less lollipop to choose from. And you do it for each child, and then you get 0 lollipops left over. And just going back to fundamentals here, what does n choose r actually mean? It can be easy to forget there's an actual formula, and this means that you don't require a calculator to actually simplify this. So there was a similar question on the lab test too, in which it was like rolling die, and in the end it all simplified, and this is the same style, right? You can see clearly this is going to simplify, and this will simplify, and this will simplify, and we can observe that once it's all simplified, I should get this, which once again is similar to, there can be other questions similar to this. It's in the lab test it was 2 people roll exactly 2 people roll a 2, exactly 3 people roll a 3, and so on. And then you'd have something like this in the end. So this is a similar question. And of course now we just have to reapply both of these 2 different questions and combining our answer into one. So we're just multiplying again, should be quite straightforward. Okay, and now this is kind of building on the work they were doing earlier with the at least 1 ball. So how many solutions are there with all the xi being odd, and xi is less than or equal to 7. So being odd, this is probably something you haven't come across before. But just remember that odd numbers are just even numbers plus 1, right? So how we will define that, I mean, even numbers obviously just an integer multiplied by 2. So the way that we define the odd numbers is just in this form. Right, so this idea of odd numbers being described as an even plus 1 will probably come out, throughout like any topic, so just keep that in mind. And therefore, so xi is greater than 1. I think this is all, should be able to understand that. And of course we have to apply this second requirement, but that's quite easy to do. You just sub in, and we can see y is less than or equal to 3. So then we can just substitute in, and what we'll find is that we eventually receive this form here, but we still have to, this is our odd requirement, and we still have to deal with the less than or equal to 7 requirement. So yeah, this is just going what I said before about the at least one bool thing. Like, you're just subbing in for each individual xi, and then we can just simplify the equation to get this. So I think that's straightforward. And yeah, so now we can kind of rewrite our question as this. Now that it's in this form, it's a much more familiar form, and obviously this is the converted of x is less than or equal to 7. So moving on. Usually what we do when we're working out this less than or equal to, what we find is the total minus the greater than. That is the traditional way that we do it. So first we just find the total, and this is the total, right, because we're using 15 here, and there's 6 y's, so then using the same formula from before, you'll be familiar with this formula. That's our total. And now we have to divide into the different cases in which there is the different cases in which a yi is greater than or equal to 4. So there's 1, we have to divide into the cases 1, which is greater than 4, and then 2, which is greater than 4, and then 3. And so we treat these cases differently. And also, obviously, 15 objects, you can't have 4 yi being greater than 4. Right, so this is going to be the case in which 1 is greater than or equal to 4. And remember, if one of the yi's is greater than or equal to 4, we can just rewrite it as another non-negative integer plus 4, and that will guarantee that it's always greater than 4. We can sub it. Technically you don't have to replace every other one. It's still like the same. It's still going to be the same like principle and formula if these remained as y2s and y3s. But yeah, so this is the case in which one of the y's is greater than 4, and then once again we reapply the formula, and that's our number of solutions for 1, and then we just repeat this process again for 2. So we've just subbed in y1 and y2, and we get 7. Apply the formula again, and then we repeat the exact same thing again. And this is the number of solutions. But now we have to find a way to make sure that what we're going to be adding and subtracting from the total is actually representative, is actually correct. So if you haven't seen this before, it can be a little bit intimidating, but at the most basic level, imagine we had, I don't have much space, but imagine we had like a Venn diagram, right? It's like this. And you count each circle once, right? Now that means that you've counted these sections 2 times and this section 3 times. So obviously that's not representative of your total. So then you want to subtract the intersections, right? So you want to subtract the red, right? But if you subtract the red 3 times, well, each red, right? And the red includes this middle part here as well. So what you'll find is that, yes, you would have counted this section once, and you would have counted this section once, right? If you subtract it once and once, but then this will be counted 0 times if you, in order to make this only counted as once, which means that you need to add this part again, right? So now you have to add the blue. So this principle, the inclusion and exclusion principle, is just about making sure what you're counting is actually representative. And the key here is that whether or not you're adding or subtracting, it changes like each time. So you'll be adding for one lot, and then you'll be subtracting, and so forth. So applying this to our question. I think that's explanatory. We can also, yep. So we have to apply this, and also note. Okay, well, I think we'll just ignore this. No, we should use that. So, basically, this is representing like. Well, we've chosen, in this case, in A1, this is the case in which we've selected one of them to be greater than 4, right? So we've there's six y values, and we've chosen one of them to be greater than 4, greater than or equal to 4. And then the next case, we have to multiply by 6, choose 2, because we've chosen 2 of them. And in the next case, we've chosen 3 of them, so we have to choose 3. So that's why we've multiplied by these terms here, right? And yeah, so this is just applying the inclusion and exclusion principle. So the total will be equal to, this first one minus the intersection between 2, add the intersection between 3, and we only got to 3 times, so that's all we have to worry about. So once we've put it into our formula, then we have to remember that, well, what we're actually looking for is because this is representative of y is greater than or equal to 4, and then this is the total, right? But what we're trying to find is less than or equal to 3, so we just do the total minus the solutions in which it is greater than or equal to 4, and therefore we just subtract this whole term here, and we'll get our number of solutions. So yeah, hopefully that's straightforward. You're just like alternating these addition and subtraction, and you choose 1 to be greater than 4, you choose 2 to be greater than 4, you choose 3 to be greater than 4, that's why you multiply there. And then the rest of these terms are just the terms which we've calculated just above. So 8, yeah, 16, 12, 8. Right, so hopefully that makes sense. And now we'll be moving on to some traditional perms and coms. So this is the full question. We'll just move on to the question A. So how many words are there altogether? We see in the question here, no letters used more than once, so there's no repetition. So we can just apply the permutation. So 26. Just note that it's not, it doesn't actually have to form like a English word or something, right? It's just symbols, right? And you're just picking 14 of them, and order does matter, right? So it's not 26C14 because order does actually matter. Right, so moving on to the next one. Contain these subwords Julia or Tony. And once again, we're going to be using like inclusion exclusion principle, right? Because if you did, Julia plus Tony, then you're going to have an intersection, and you would be counting these words twice. So that's essentially the basis of this question. It's going to be this line here. So we have to find all 3 of these terms. Yep. Okay. So let's just break it up and first start with Julia. So to find the words with Julia, so we just plug in Julia, and of course we want to maintain this order. So and we've got 14 letters, right? So we've used 5, we've got 9 left, and we've used 5 letters, so we've got 21 letters available left. That just means that first we'll break it up and we'll just choose. It's just easy to think and break up. So we'll just choose the 9 letters, which is this many ways, right? We've got 21 letters and 9 spaces left. And then we just treat Julia as if it is one object, essentially, or one letter, you could say. So in this case, we have 10 objects, right? We've got the 9 here, and we've got the 1 Julia. So it's just going to be 10 factorial arrangements for this. And we just multiply that together, and that will give us our answer. And we're just going to be repeating the same process with Tony. So once again, we've used 4 spaces, and we've used 4 letters, and then we choose the remaining letters. And then we just treat Tony as one object, one letter, and we find all the arrangements, 11 factorial, 10 letters plus this one Tony, and we multiply that together, that's how many words we get. And then now we'll just be very similar thing again, we just apply to find and. So we just plugged it in, same process, fill in what's left, treat each of these words as one object, and of course that means 5 letters and one object here, so it's going to be 7 factorial arrangements multiplied by the choices for the letters, and then that will give us how many words are with Julia and Tony. And then we just use the inclusion-exclusion principle. Yeah, just think about it. You will be counting the intersection twice, so you have to subtract it once. So we just fill in with the answers that we've gotten so far, and that will give us how many words there are with Julia or Tony. Okay, next question, how many words contain all 5 vowels? So it's just containing, so we just get to choose we just choose the 5 vowels, right, and we just put them as available to be selected. And then we choose another, obviously, it's kind of similar to before, we choose 9 of the 21 remaining letters. And because beforehand we had to preserve the order of Julia, so we just treat it as one object, right? But now, because all the requirement is that we contain the 5 vowels, so it doesn't actually matter. We can treat each vowel individually, so it's just a normal question, and it's 14 factorial for the 14 letters. And then remember to just multiply again. Right, so moving on to the next question. So finding the probability, so this is going to be the number of certain cases divided by the total cases. So, hopefully you know what a deck of cards is. I think they tell you if you don't know the exact layout, they describe what it is. So it's like between Julian and Wayne. They've been dealt all 13 spades. Obviously, first I guess you can work out the total cases. So it's just 52 choose 26. There's two players, so you're choosing 26 cards, and 52 playing cards are available. So what you do is you can just autofill the 13 of the 26 cards that they can get with the spades, and then you just calculate like how many remaining are left, how many remaining cases are left, which is much easier to think about, other than like trying to create each combination. So we selected all the spades, so we've just got 39 cards left, and then we're only choosing 13 left, because we've already chosen 13 as the spades of the 26. So now we just do the probability, which is the number of cases with requirement over the total cases. And that's straightforward. Find the probability that the cards dealt to June and Wayne contain at least one complete suite. So we can just build on what we've done in A. So, and at least one, it's clear that it's possible to get 2 as well, so you have to keep that in mind. And obviously there's no way to get 3 or more complete suits. So the way we can do this is, once again, the inclusion-exclusion principle. So the reason why this is, so this is like we've chosen one of the suits. So we'll choose one, right? Like you choose 1 spade or 1 heart or 1 club, or you choosing 1, and then you're multiplying by like the cases of the requirement. And then the next case is in which you've chosen 2. So you've chosen spades and clubs, or hearts and clubs, or whatever. So that's why it's 4 choose 2, and it's times 1 here because, well, if we're applying the same principle to how we got this, right? 52 cards available, and you're choosing 26, right? And you can see here that we've like subtracted 13. Obviously, if we've chosen 2 suits, then this will just become 26 choose 0. There's an arrow. Yep. So that's why that's 1 there, because there's only like one manner in which there's only one case in which this occurs, because there are no remaining cards to select from. So that's why that's 1. And yeah, that's just your answer in the end, or the number of cases, and then you just divide by the total cases again. Same principle. I don't know if I don't think we're doing question B, but yeah, we'll just see. Okay, so question A. Write B in terms of A in. Right. Yeah, so there's only 2 cases, and that is either it does have an odd number, or it does have an even number. So if you add these together, it will give you the total, right? And we can represent this. They've given you like the digits available. There's no 0, right? So each gap will only have 9 options. And yes, with repetition. Right. So the sum of the ones with odd and this, with the amount which has an even number of prime digits is obviously just going to be equal to the total number of such numbers, which in this case is 9 to the n, right, where n is the number of digits. Hopefully that makes sense. So like the first option you have 9, and then second, and so forth. So write Bn in terms of A is our question, so this is going to be our answer. Let me just... Oh yes. Yep. Okay, so now we need a recurrence relation, but we don't need to solve the recurrence relation. So let's just consider like the n minus 1 will be n minus 1 digits. So yeah, so the nth digit must not be prime in order to count towards an. So, I mean, looking at our thing, 5, 1, 2, 3. Oh, sorry. So not prime digits. 1, 4, 6, 8, 9. That's how we get our 5 digits. And then this next is that the next requirement is that in the case of being -1, in order for count towards a n, the nth digit must be prime. Like the next one that we're going to count, the next digit we add is prime, and there's 4 prime numbers. So this is how we've gotten these results here, 4 and 5. And this fits into our recurrence relation. So once again, we've got the 5 from the 5 non-prime numbers, and the 4 from the prime numbers. And then we use our solution to question A, which was that b to the, bn equals 9n minus a. So we just sub in, and then we can get rid of the b in -1 term, and it boils down to this. So yeah, you're just applying, you're just thinking of the case in which the nth, you just set the nth digit to be not prime. Not prime in the case of this an, and the requirement for it to be prime when you're dealing with bn -1. Anyway, next up we've got a recurrence relation. This is a bit of a nasty recurrence relation. So we'll just quickly cover this, what actually is a recurrence relation. Like the descriptions of it: linear, homogeneous, and non-homogeneous. So looking at our one, it's pretty nasty. And, oh yes, this is also important. So we can just find how to describe our equation, because you will need to find the particular solution, or like suggest a particular solution, and then if it's shared in the h, then we have to multiply by n until eventually we find a particular solution which does not share any terms with hn. So going back to ours, this is non-homogeneous, and it's linear, and second order. Right. Ooh, okay, so we just start off with the default one where we're looking at we just find solutions to this quadratic, right? This is the first step, as always. We find that it's squared, which is not nice. Makes things a bit harder. Because now this means that our general solution will be in this form. With the notable thing being that's multiplied by n here. And now we have to choose our particular solution, right? And remember that before, if we have shared terms with hn and p in the particular solution, then we have to multiply again by n until eventually we don't share any terms. So we can try. Initially we try, something simple. Well, we see that obviously it shares both terms with the general solution. So it does not work. So we have to multiply by n again. But we see that this term here is also shared in the general solution, so we have to multiply by n again. Which leads us to get this form, which is not very nice. And now we have finally found a form in which we do not share, a form for the particular solution in which we do not share any terms with the general solution. So now we just sub in the particular solution into this, right? So in here we've just multiplied in the bracket, and each n, this n minus 1 obviously becomes n minus 1, and the same thing for n minus 2. So after a lot of very careful manipulation, we can eventually equate coefficients. So the first step here, if you're not sure where to go from this line, I divide by 3 n minus 2. So you'll be left with like a 9 here, and they'll be cancelled out and so on. I believe that's correct. And then yeah, that is correct, yeah. That becomes 3. This becomes 9. And then you expand, and yes, it will be annoying. Just don't make a mistake, and you'll be fine. And then eventually it simplifies all nicely into this, and hopefully you've learned the technique of equating coefficients. You can see like the n term here is 5 and 6c on the other side, and eventually we can just solve these simultaneous equations and sub back in, and we found our particular solution. So now we know this. This is actually the end of the question, but if it had continued, maybe they would give you like a0 equals something and a1 equals something, and then you just sub in, of course, with the respective n, and you can solve for a and b. But in this case, they haven't asked that. So yeah, so that's it for this seminar. Yeah, apologies that this last topic 4, was all the same as the 2022 Term 3 one, but regardless, try your best, do well. Thanks for watching, and hopefully you can see what you're really capable of in the exam.